Well, I think you'll enjoy finding the area between polar curves, or at least bounded by a polar curve, much more than you did finding the slope of the polar curve at the point. The most recent video I did was this big mess where we had to find the slope of the curve at the point, and you had to come up with all of that. So you should have already watched that video. And let's go ahead and remember what we did back in Cartesian coordinates. So again, this video, I'm going to explain how to find the area bounded by a polar curve or by more than one polar curve. In this particular video, just one. But it's easier to explain how to find the area between polar curves by relating it to in Cartesian coordinates when we have y as a function of x. And way back when we wanted to find the area of the region bounded by the curve y equals f of x and the x-axis in between a and b. So this is our thing we wanted to do. And then what we did was we built a rectangle. All we needed was 1, and we needed the dimensions of the rectangle. Okay, so the area of the rectangle was equal to the length times the width. Well, okay, so we knew that way back when, but the length of this would be the height, actually. So we call it the length anyway. The height from the x-axis all the way to the curve, we define that to be our f of x. So the length is our f of x, and then our little width right there was our change in x. Okay, so we just said that's dx. So the area then, total area between the curve and the x-axis, in between or on the interval from a to b, was equal to the integral from a to b of the length times the width, so the area of one rectangle. So if we integrate, we're adding up an infinite number of things. And when we integrate from a to b, the area of one rectangle, we're adding up the areas of an infinite number of rectangles from a to b. And that's the area. Okay, so we have length times width of one rectangle. Okay. Well, I wanted to put the polar coordinates over here, but I'll do that right underneath here. Let's make a little subheading here. So we're going to go with polar coordinates. Okay, so let's do that. So let's relate these. Let's see if I can squeeze that in there. Okay, well in polar coordinates, we could still draw an x and a y axis, but we're going to have this curve swept out here, and it doesn't necessarily have to be circular like that. It could be kind of curvy like that. Anyway, we want to define our interval. Instead of from a to b, we're going to integrate, we're going to define the area, I should say, from theta 1, so an angle of theta, we'll call it theta 1 to theta 2. And we could call it alpha to beta. Probably should have used alpha to beta, but I'm already committed here. So anyway, what we want to do is instead of drawing a rectangle, that wouldn't make sense here, we're going to draw a sector. So we talked about a sector the other day in class. Okay, so we're going to make one sector. Okay, and that sector is going to have a radius here, so r. Okay, and by the way, I didn't define this, but this curve here is r. Instead of y equaling f of x, we have r equaling f of theta. Okay, so that's what this curve is. This is r equals f of theta on the interval from theta 1 to theta 2. Okay, and we have this sector, and the sector has a little change in theta, like that, a change in theta from here to here. Okay, that's analogous to the change in x here, so we have a change in theta. And the area then of, remember, the area of one sector is 1/2 r squared, and the theta, though, is so small, it's just a change in theta. Okay, so the area of one of these little wedges is 1/2 r squared d theta. Okay, so that's the area. Like I said, we had the area of the rectangle is length times width. The area of one of these rectangles is f of x dx. Well, the area of this sector is r here, times the 1/2 r squared times the d theta. Okay, and so therefore the area, total area, and when I say total area, I mean all this area right here, okay, between theta 1 and theta 2 would be equal to, we're going to sweep out an entire region we're going to add up an infinite number of sector areas, okay, from theta 1 to theta 2 of the area of one of those wedges, or one of those little mini sectors, and that is your area formula. Okay, so that's your area formula in polar. So let's look at some examples. Okay, let's go ahead and just use this here example. Okay, and find the area of r equaling, let's say 1 plus, let's use that same function because we know what it looks like. Okay, so we have r equals 1 plus cosine of theta, and we know from experience, let me do this here. Let's make that 1/2, 1, 3/2, and 2. I wanted it a little bit bigger so we can see the sectors a little bit better. Okay, so there's 1/2 there, and then we have -1 down there. Okay, so we're going to draw the graph. Okay, and it comes up like that. Hits here. Okay, and we want the area of the entire region. Okay, so we want all this. Let's do it in the same color. That's all this. Okay. So if we want the area of all that, we have to figure out, well, first of all, where does our theta 1 start? Well, if you remember, stuff I wanted you to have dialed in by now would be, where do we start here? If we start at theta equals 0, then we're right here, because r is equal to 2. So 1 plus cosine of 0 is 1, 1 plus 1 is 2, so we start here. So our first sector, so that's our theta 1 right there, okay? And that's where our first sector would go. And then when theta increases, you know that, remember, r and theta have direction, okay? So this is what's happening all the way around the curve, okay? So as theta increases, we're sweeping out this entire region. Now the hard part is to visualize this, but I'm going to show you a cool visual in class, okay? So if you're having a hard time now, don't worry. But the sectors go all the way from 0 and then pi, and then they keep going. They start getting bigger again. They sweep out the entire region all the way there, and then once you get the region swept out, you go, okay, well, where did we end? What was the theta that we ended at? When do we start over here? Well, that's theta equaling 2 pi. 2 pi, we're back to 2 again, so that's your theta 2. Okay, and so the area then, all we have to do really is find our r, which we already found, and we find our theta 1 and our theta 2. Well, the area then would be the integral from 0 to 2 pi of 1/2 r squared, so r would be 1 plus cosine theta squared. Don't forget the squared, everybody forgets that, d theta. Okay, and you're just going to punch that into your calculator. Okay, we can do this by hand, but I'm not going to make you do it by hand. I want you to focus on the concept here. So punch that into your calculator, and where's my calculator? Okay, so we're going to fancy ones now. So we go, we don't necessarily need to be in polar mode now, so let's put ourselves back in function mode, because remember, on any integral, that variable there is a dummy variable, so we can use any variable at all. Okay, that's a dummy variable. Okay, so this guy right here. So anyway, we can go ahead and define our y1 to be, and I like to do this first. I like to make sure that my integrand is y1, because otherwise I'm going to forget that squared. That's really going to bother me. So I'm going to go 0.5, and we're going to multiply 0.5 by 1 plus cosine of theta, or in this case that's going to be x, so because I'm in function mode. Okay, and I'm going to square that. So I know now I can double check here. 1 plus cosine of x squared, that's consistent with what we have here. And quit that. Now I'm going to double check and make sure I'm in radian mode. Yeah, I'm in radian mode. Anytime I'm dealing with anything in calculus really is going to be radian mode. So second, quit that. And now I can go ahead and math 9. I'm going to integrate from 0 to 2 pi. And then I know that this is my y1. Okay? Bars, y variables, y1, enter. Okay, and dx. And so we get, takes a little while here, 4.712. So there we go, 4.712. Okay, and let's see, maybe we can do another one. Let's try another one. I think it's kind of fun to do this. Okay, so let's go with r is equal to 3. Okay, so you should know by now that r equals 3 is a circle, center at the origin. Okay. And this is kind of fun because we already know what the area is. The area is pi times r squared. So it's pi times 3 squared, so 9 pi. Okay, but watch. This is kind of cool. We know that it takes, if we look at r theta, if theta equals 0, r is 3. Okay, pi over 2, 3. Okay, pi, 3 pi over 2, and 2 pi. So where we start is our theta 1. Where we end is our theta 2. So this is kind of an interesting one because we know what the answer is already. But we're going to sweep out. Remember, we're going to sweep out. We're going to draw one sector. Okay, the d theta is this guy right here in the middle, and the r is 3. Okay, well again, we just use our formula. And why am I doing this? Because it's fun to show you that the formula actually works even when you don't need to use the formula. So the area, or the integral from 0 to 2 pi of 1/2 r squared. Okay, so r is 3 squared d theta. Okay, and so we have 9/2 times the integral is from 0 to 2 pi of d theta. Well, we can do this by hand, right? So we go 9/2 times, and then what do we write here? What's the antiderivative of 1 d theta? Well, the antiderivative of 1 d theta is theta. Okay, from 2 pi, from 0 to 2 pi. Okay, and so we have 9/2 times 2 pi n for theta, 2 pi, minus 0 n for theta. Okay, and so we see that 9/2 times 2 pi is 9 pi. So 9 pi either way, so the area of a circle, you can get it by using the formula, which is what you would always do, or just wanted you to see it in action here, the area using the polar formula for the area. Okay, and then it should be enough there for you to go ahead and do a couple of those area problems in the book, and then we can practice some more in class. One more video on arc length.